SDR's DRAM standard ever approved by the JEDEC, and delivers a bandwidth of 1.066 GB per second, 133.33 MHz *64/8 equals 1.066 GB/s. 1 GB/s equals 1 billion bytes per second. PC133 is backward compatible with PC100 and PC66.DDR. While the access latency of DRAM is fundamentally limited by the DRAM array, DRAM has very high potential bandwidth because each internal read is actually a row of many thousands of bits. To make more of this bandwidth available to users, a double data rate interface was developed. This uses the same commands, accepted once per cycle, but reads or writes 2 words of data per clock cycle. The DDR interface accomplishes this by reading and writing data on both the rising and falling edges of the clock signal. In addition, some minor changes to the SDR interface timing were made in hindsight, and the supply voltage was reduced from 3.3 to 2.5 V. As a result, DDR's DRAM is not backwards compatible with SDR's DRAM. DDR's DRAM, sometimes called DDR1 for greater clarity, doubles the minimum read or write unit. Every access refers to at least 2 consecutive words. Typical DDR's DRAM clock rates are 133, 166 and 200 MHz, 7.5, 6, and 5 ns/cycle, generally described as DDR 266, DDR 333 and DDR 400, 3.75, 3, and 2.5 ns per beat. Corresponding 184-pin DIMMs are known as PC2100, PC2700 and PC3200. Performance up to DDR 550, PC4400, is available. DDR2. DDR2's DRAM is very similar to DDR's DRAM, but doubles the minimum read or write unit again, to 4 consecutive words. The bus protocol was also simplified to allow higher performance operation. In particular, the burst terminate command is deleted. This allows the bus rate of this DRAM to be doubled without increasing the clock rate of internal RAM operations. Instead, internal operations are performed in units 4 times as wide as SDRAM. Also, an extra bank address pin, BA2, was added to allow 8 banks on large RAM chips. Typical DDR2's DRAM clock rates are 200, 266, 333 or 400 MHz, periods of 5, 3.75, 3 and 2.5 ns, generally described as DDR2-400, DDR2-533, DDR2-667 and DDR2-800, periods of 2.5, 1.875, 1.5 and 1.25 ns. Corresponding 240-pin DIMMs are known as PC2-3200 through PC2-6400. DDR2's DRAM is now available at a clock rate of 533 MHz, generally described as DDR2-1066, and the corresponding DIMMs are known as PC2-8500, also named PC2-8600 depending on the manufacturer. Performance up to DDR2-1250, PC2-10000, is available. Note that because internal operations are at a half the clock rate, DDR2-400 memory, internal clock rate 100 MHz, has somewhat higher latency than DDR400, internal clock rate 200 MHz. DDR3. DDR3 continues the trend, doubling the minimum read or write unit to 8 consecutive words. This allows another doubling of bandwidth and external bus rate without having to change the clock rate of internal operations, just fewidth. To maintain 800/1600M transfers /s, both edges of a 400/800 MHz clock, the internal RAM array has to perform 100/200M fetches per second. Again, with every doubling, the downside is the increased latency. As with all DDR's DRAM generations, commands are still restricted to one clock edge and command latencies are given in terms of clock cycles, which are half the speed of the usually quoted transfer rate. A CAS latency of 8 with DDR3-800 is 8/400 MHz, equals 20 ns, exactly the same latency of CAS2 on PC100 SDR's DRAM. DDR3 memory chips are being made commercially, 15, and computer systems using them were available from the second half of 2007, 16, with significant usage from 2008 onwards. 17, initial clock rates were 400 and 533 MHz, which are described as DDR3-800 and DDR3-1066. PC3-6400 and PC3-8500 modules, but 667 and 800 MHz described as DDR3-1333 and DDR3-1600. PC3-10600 and PC3-12800 modules are now common. 18. Performance up to DDR3-2800. PC3-22400 modules are available. 19. DDR4. DDR4's DRAM is the successor to DDR3's DRAM. It was revealed at the Intel Developer Forum in San Francisco in 2008, and was due to be released to market during 2011. The timing varied considerably during its development. It was originally expected to be released in 2012, 20, and later, during 2010, expected to be released in 2015, 21, before. Samples were announced in early 2011 and manufacturers began to announce that commercial production and release to market was anticipated in 2012. DDR4 reached mass market adoption around 2015, which is comparable with the approximately 5 years taken for DDR3 to achieve mass market transition over DDR2. The DDR4 chips run at 1.2V or less, 22, 23, compared to the 1.5V of DDR3 chips, and have in excess of 2 billion data transfers per second. They were expected to be introduced at frequency rates of 2133 MHz, estimated to rise to a potential 4266 MHz, 24, and lowered voltage of 1.05V, 25. By 2013. DDR4 did not double the internal prefetch width again, but uses the same 8N prefetch as DDR3. 26. Thus, it will be necessary to interleave reads from several banks to keep the data bus busy. In February 2009, Samsung validated 40nm DRAM chips, considered a significant step towards DDR4 development. 27. Since, as of 2009, current DRAM chips were only beginning to migrate to a 50nm process. 28. In January 2011, Samsung announced the completion and release for testing of a 30nm 2048MB 6 DDR4 DRA module. It has a maximum bandwidth of 2.13 bit /s at 1.2V, uses pseudo-open drain technology and draws 40% less power than an equivalent DDR3 module. 29, 30, DDR5. In March 2017, Chedek announced a DDR5 standard is under development, 31, but provided no details except for the goals of doubling the bandwidth of DDR4, reducing power consumption, and publishing the standard in 2018. Their standard was released on the 14th of July 2020. 32 failed successors. In addition to DDR, there were several other proposed memory technologies to succeed SDR's DRAM. Rambus DRAM, a DRAM. A DRAM was a proprietary technology that competed against DDR. Its relatively high price and disappointing performance, resulting from high latencies and a narrow 16-bit data channel versus DDR's 64-bit channel, caused it to lose the race to succeed SDR DRAM. Synchronous link DRAM, SO-DRAM. SO-DRAM boasted higher performance and competed against a DRAM. It was developed during the late 1990s by the SLDRAM consortium. The SO-DRAM consortium consisted of about 20 major DRAM and computer industry manufacturers. The SO-DRAM consortium became incorporated as SO-DRAM Incorporated and then changed its name to Advanced Memory International, Inc. SO-DRAM was an open standard and did not require licensing fees. Their specifications called for a 64-bit bus running at a 200, 300 or 400 MHz clock frequency. This is achieved by all signals being on the same line and thereby avoiding the synchronization time of multiple lines. Like DDR's DRAM, SO-DRAM uses a double-pumped bus, giving it an effective speed of 400, 33, 600, 34, or 800 mount/s. 1 mount/s equals 1000 transfers per second. SO-DRAM used an 11-bit command bus, 10 command bits CA9:0 plus 1 start of command flag line, to transmit 40-bit command packets on 4 consecutive edges of a differential command clock, CCLK/CCLK hash. Unlike SDRAM, there were no per-chip select signals. Each chip was assigned an ID when reset, and the command contained the ID of chip that should process it. Data was transferred in 4 or 8 word bursts across an 18-bit per-chip data bus, using GON of 2 differential data clocks, DCLK0/DCLK0 hash and DCLK1/DCLK1 hash. Unlike standard SDRAM, the clock was generated by a data source, the SO-DRAM chip in the case of a read operation, and transmitted in the same direction as the data, greatly reducing data skew. To avoid the need for a pause when the source of the DCLK changes, each command specified which DCLK pair it would use. 35. The basic read/write command consisted of, beginning with CA9 of the first word. SO-DRAM read, write or row op request packet FLAG CA9 CA8 CA7 CA6 CA5 CA4 CA3 CA2 CA1 CA01 ID device edit 0 CMD50 command code CMD0 bank row 0 row, continued, 00000 column. 9 bits of device ID. 6 bits of command. 3 bits of bank address. 10 or 11 bits of row address. 5 or 4 bits spare for row or column expansion. 7 bits of column address. Individual devices had 8-bit IDs. The 9th bit of the ID sent in commands was used to address multiple devices. An aligned power of 2-sized group could be addressed. If the transmitted bit was set, all least significant bits up to and including the least significant 0 bit of the transmitted address were ignored for "is this addressed to me?" purposes. If ID 8-bit is actually considered less significant than ID 0, the unicast address matching becomes a special case of this pattern. A read/write command had them bit clear CMD5 equals 0. CMD4 equals 1 to open.
Yes, I need a break. I need a break because I not understand this, and we have recorded like 1 hour. I need a break because I'm just close to fall asleep. Not because I think this is super boring. It's not why. That's because I not sleep so much tonight and it's very hot in my apartment. So I'll take a break and start upload this. It's 30 degrees in my apartment and it makes me very sleepy. So let's just start to upload this and just continue. Maybe my cola is a little bit cold. I can drink a bit cola. But let's take some juice because I'm going to eat this soon. Cola and bread is probably not that good. No, I don't think it's boring. It's just me. I'm sleepy and it's payday today. I've been outside 2 times today in shopping. And I have to pay a lot of money tomorrow. But I have the money ready tomorrow to arrange this apartment and my debts. But I have not paid my rent yet. So actually, if I not pay my rent tomorrow, I will be homeless. I don't have a saving. I don't have a saving few $100. So that was a little bit stupid. I buy a new computer like $100, but I did that because that was Acer. Acer expired the 4th generation. This is the 1st generation. Yes, but I need a break. I will upload this and charge the camcorder a little bit.